Welcome, everyone. I'm Dan Grossman, longtime faculty member in the Programming Languages and Software Engineering group. It occurred to me earlier today that I've hosted any number of colloquia in computer science and engineering over the years, but this is the first time I haven't been wearing shoes. We have 4 great talks today that we'll hear from. What we'd like to do is go ahead and go through all of the talks. If you have questions for any of the speakers, you can go ahead and queue them up in the chat, and I'll try to keep track of them and call on you, but after all the talks. So we'll do the 4 talks, and then you can address your pre-queued up question to the relevant speaker. The talks are not connected in any particular way, other than they're all from some of a strict subset of amazing graduate students working in the group. And we'll start with Max Wilsey, who's going to tell us about eGraphs and some of the cool things you can do with them.
Thanks, Dan. This is likewise my first talk that I've given without shoes on. I'm going to tell you about some work I've been doing with all these wonderful people listed down below. And hopefully by the end, you will know that eGraphs are good based on this tool we've been working on called Egg. So before we dive into eGraphs, let's just talk about expressions. In a lot of computing, especially in programming languages, basically all we do is manipulate expressions. We try to turn expressions into better expressions, or show 2 expressions are similar or relate to expressions in some way. So here's an expression from could be any language, but right now we're just going to talk about kind of the language of mathematics because it's one we're all familiar with. So this is a times 2 divided by 2. And if I was writing a compiler for math or something, one thing that I might want to do is show that come up with a better way to write this. This is rather inefficient to compute, as we can all see. It's rather silly. This is obviously just a, so you might want to figure that out. Another thing that you might want to do is if you have both of these as an input, is show that they are the same. Given both as an input, show that they are equal. So these are really old problems in programming languages and computing. The first one is kind of optimizing a program, and this asking equivalence question is really common in verification or program synthesis. So how do people do this? One really common way is by using term rewriting. And so to do a term rewriting, you come up with a bunch of equalities. We're going to call them rules. And you basically use them like rewrite rules. You'll look at the equality and you'll try to see if one side matches a part of your expression, and then you replace it with the other side. So here, I've written some rules that I will call useful because these rules will get us from a times 2 divided by 2 all the way down to a. This is our optimization problem for now. But there are also a bunch of other equalities over the language of mathematics. And here are some that I've conspicuously named not so useful, and we'll see why these are less useful in this context in just a minute. But first, let's see how we would do rewriting with the useful rules. So we start with our initial input. And again, this is a times 2 divided by 2. And the first thing that we have to do, if I asked you to simplify this by hand, probably the first thing that you would do is apply this top rule, right? You have to reassociate this multiplication with this division, okay? Now that we've done that, we can see that our identity rule, the second rule, matches on this inner 2 divided by 2. So we write that to a 1. And then finally, we can use the cancellation rule, which is the bottom one, and get to our final goal here, which is A. So that's great. Those are the useful rules. I labeled them useful, obviously, because these are the rules that you would use if you did this by hand. But what about the not so useful rules? Why are they not so useful? So let's take this first rule, for example, which is x times 2 goes to x left shift 1. Now, this is a rule that's useful in a lot of contexts. This is a rule like this is probably in every modern compiler because bit shifting is really cheap compared to multiplication. But in this case, this would be a really poor choice of a rewrite to make. In particular, you would perform the rewrite and you replace that multiplication with a shift, and then you'd kind of get stuck, right? This is a bad path, right? You've made the expression better. It's probably cheaper to compute this part with the shift, but this prevents you from getting to your ultimate goal, which is, of course, seeing that those 2 things cancel out. What are some other problematic rules? So the second rule that I've listed is commutativity. That's one we all know, and we've probably used, when we do math by hand. But one problem is if you start applying this computationally, you can easily get in a loop, right? We've flip-flopped this 2 and this A, and we flipped them back. And that's, not super useful. And likewise, this identity rule written the other way can also kind of get you into a little bit of a loop. Here, instead of getting you back to where we started, we're producing infinite sized terms or arbitrarily sized terms. And that's, obviously no good. You don't want to just create infinite sized terms for no reason. So again, these rules are not useful in this context for this particular problem of rewriting, A times 2 divided by 2 to A. Many of these rules are critical for other inputs. Obviously, compilers are doing this bit shifting rule all the time because that's a really fast way to compute things. And more importantly, these rewrites will, in other contexts, enable other rules. Sometimes you'll need to perform, commutation before you can, see that another rewrite matches. So this kind of raises this question, right? Which rewrite do you apply when? Here I've helpfully labeled, which rules are useful and not useful, but obviously you don't have that when you're building a term rewriter. So how do you know which rewrites are useful for a given problem? And more importantly, the order is also really important. If you apply the wrong rule at the wrong time, you can easily get stuck. So this problem is really hard in general. It's called the phase ordering problem in optimizing compilers. And people have a bunch of different solutions. One that you could kind of imagine is maybe you do like a sort of search procedure where you try some rewrites, and if you get stuck, you back up, and then you try some different rewrites and maybe in a different direction. But I'm going to propose a different solution, and that is we just apply all of the rewrites all the time. We basically track every possible expression that you could possibly create from the rewrites. And this is obviously great because you're not going to miss anything, but it probably sounds slow. And let's see, how we can do this in a way that's not so slow. So this is where egraphs come into play. So here we've got an egraph on the left and a little bit of a legend on the bottom. An egraph is basically a set of equivalence classes, E classes. And inside those classes, there are E nodes. And these E nodes are basically operators from our language. And here you can see this top E class represents, we use the term represents to say it kind of holds the term, A times 2 divided by 2. This is the same term as before. And if you kind of follow those edges that go from E node to E class, you can kind of see how this E graph looks a lot like a term graph, which we use to represent programs. But this is basically where the similarity between E graphs and term graphs end, because we could do rewriting over the E graphs in a pretty neat way. So let's take that, problematic in this context rewrite, and let's try it. So we can look over our E graph for anything that matches X times 2. And, of course, we see the A times 2. And we apply it. And in this context, what that means is we make a new E node that represents the left shift, and we put it in the same equivalence class as the times. And what that means is that we now have a choice on how to write that subterm, right? We can either write it as A times 2 or A shift 1. And those, of course, are equivalent. And that's really great because, we got a little sharing. We didn't duplicate A, and that's cool. But it also propagates up. So we can see that this division node now represents multiple ways to write our original term. So that's pretty cool. And the big takeaway here is that this rewrite didn't destroy anything. It only added information to the E graph. And we could keep doing this. We could keep applying rewrites. And notice how we're only adding more nodes to the graph. We don't really have to follow this part. In fact, sometimes you could see this final E graph applies the identity and the cancellation rule. It actually made the E graph smaller, which is kind of neat. We reduced the number of E classes and didn't add any E nodes, but we added information to the graph. It knows about more equalities. In fact, this E graph, because there's a cycle in it, also represents an infinite number of terms. It represents A and A times 1 and A times 1 times 1. So E graphs are really compact at representing these large sets of equivalent terms. E graphs can also fill up. So if we tried to run these rewrites again against this, this final E graph, we would notice that nothing happened. We didn't add any more information. So you could tell that you're done. In fact, in this case, we know that we have learned every possible fact that we could possibly know given these axioms in this E graph. So that's a pretty neat thing. And basically, this style of rewriting has recently been put together in this algorithm called equality saturation, which is used for program optimization. Basically, you take an input term and you chunk it in an E graph, and you crank some of those rewrites, as I just showed you, and you get your optimized term out. And let's dive into that rewriting loop just a little bit. The way that this typically works is, you find a pattern, you search for that left-hand side of a rewrite, oops, and then you apply the right-hand side. You put it in the eGraph as I showed you. But then the eGraph has to do this part called invariant maintenance. And this turns out is actually really expensive. One of the invariants that an eGraph maintains is congruence. And congruence is really great because it helps you find more equalities. But the way in which the eGraphs were maintaining this was really expensive. It was taking up most of the runtime of this equality saturation algorithm. So one of the things that we did in our work was figure out a way to make this faster. And the way we did this was basically by clumping a bunch of the work together. So this loop runs a lot of times. How could we run it fewer times? Well, one way to do that would be to find all of the patterns and then apply all of the matches at once. And while we're applying these matches, we allow the invariants to be broken. We don't really care if the invariants are maintained in this phase. And then we restore all of the invariants at once. And this loop is going to run a lot fewer times, and we spend a lot less time overall restoring invariants, which is pretty cool. So we put all this together in a tool called Egg, which stands for eGraphs Good. And basically the takeaways are Egg is the first library that you can use to do equality saturation, which we've shown to be useful in a lot of contexts. Before, people had to hand roll it for each domain, and now you don't have to. Thanks to that technique I just showed you where we amortize that invariance maintenance, equality saturation is a lot faster than it was before. And there's some other stuff that I don't have time to talk about, but basically equality saturation used to be fixed on these syntactic rules, but now we have a way to fold in things like program analyses that make it a lot more flexible, which is cool. And we've used Egg to do a bunch of cool stuff. There's a project that came out of UW a couple of years ago called Herbie that optimizes floating point terms, makes them more accurate. We made it 3,000 times faster using Egg, which is pretty neat. A project that Remy led called Wormhole makes optimizes linear algebra kernels, and it does better than the state of the art by up to 5x, which is pretty sweet. And another project that has been using Egg is called Tensat, and it does ML compute graph optimization, and it is better than the state of the art as well. But it's also much faster at compiling. And I think one of the exciting takeaways here is this technique is not only state of the art in terms of the things that you get out of it, but it's also fast enough to put into a production compiler. And we've done it in a bunch of other domains as well. And Chandra's going to talk about one of them next. So that's Egg. There's a whole library, there's documentation, there's tutorials online, and I'm happy to talk to you about it offline if you'd like. So that's it.
Wonderful. Thank you, Max. We can all give our best virtual forms of pseudo applause while we switch over to our next screen share. So our second speaker is in fact going to be a client of equality saturation. This is Chandra Kandanandi, who's been using programming language ideas to help improve computer-aided design. Take it away, Chandra Kanna.
Cool, thanks, Dan. Hi, everyone. So today I'm going to talk about this tool that we've built called Salinsky. And Salinsky uses equality saturation and a new technique that we have invented called inverse transformations to automatically synthesize structured CAD models. And this is work that I've done with a lot of my friends here at UW and also at the Max Planck Institute in Germany. So the core thesis of this work is that designing physical objects is just like programming. And the best example of this is computational fabrication and computer-aided design, where people use a lot of different types of CAD tools for designing their models. And a lot of effort has been put into making these techniques a lot more democratized recently. And one really important way for these techniques to be democratized is to make the designs themselves more customizable and easily editable. So to give you a small example, here we have the design of a ship's wheel and a programmatic representation of this design. You can make very tiny changes to the design and get significantly different designs very quickly. And this is an advantage of having this kind of a high-level representation of a design. The problem, though, is that most of the times when people make their designs and share them in online repositories, they don't share them in that high-level format. They usually share it in these low-level triangle mesh representations, which are very standardized, but they can be really hard to work with. And for example, some of the modifications that one would like to make can be really difficult at this low-level triangle mesh level. So recently, several researchers, including ourselves, have built these mesh decompilers, which take these triangle meshes and give you back a high-level program, which is a flat program, but it is much more, it has a higher level of abstraction, so it's much more readable. And these programs are in a language that supports various 3D primitives, various affine operations, and binary operations. So this is actually a huge improvement over working with meshes, but this is not perfect. And in particular, these tools are not very good at capturing any sort of repetition in the design. And that can be problematic because if you have a complex model, for example, a gear, the flat program itself can be really long. And so it's not really any better than working with the mesh. So in this talk, I'm going to present a new tool called Selinsky. So Selinsky takes the results generated by these mesh decompilers, and it gives you a parametrized CAD program in a higher level language. And having this kind of a parametrized program lets you make these changes in very simple ways. You can sometimes even make a character change, and you can get significantly different designs very easily. So now let's look at how Selinsky works. First of all, I'm going to walk you through a very ideal input to Selinsky, and then we're going to make it more and more complex. So here we have the program that we just looked at for the ship's wheel, and we're going to use term rewriting to find a loop in this program. And term rewriting is essentially the stuff that Max was talking about in the previous talk. So the first thing we're going to do is apply a syntactic rule that rewrites this inner union of rotates into a fold expression. Fold is a functional programming feature that can be used to write loops. So once we have rewritten it to a fold, then we are going to use this algorithm called structure finding. So structure finding is an algorithm that we came up with, which takes this list of, in this case, it takes this list of rotates and it rewrites it into a map2 expression. And what that means is that now the parameters of these rotates are separated from the CAD arguments of the rotates. So as you can see here, there's two lists, and both those two lists appear under this map2 expression. And what it does is it applies the rotation to the first element of the first list and the first element of the second list, and so on. So the structure finding algorithm can be applied recursively. And once you have applied it, you can, hopefully at that point, you have separated out all the parameters of your rotate expressions in this case. And then you can send them to a custom solver. So in this case, a simple linear regression can tell you that the parameters of the rotate can be represented in a much more compact way using this formula 60 times I, right? And once you have done that, a few more syntactic rewrites can be used to sort of polish the program a little bit more, and then you can give it back to the user. So this is how Selinsky would work if the inputs to Selinsky were ideal. But the problem is that inputs to Selinsky are not usually ideal. And that's because the way mesh decompilers work, a lot of the times, the overall structure can be really obscured by mesh decompilers. So in order for this strategy to work, we'll have to do something else. So what kinds of weird things do we see in the outputs generated by mesh decompilers? So here's an example. Again, here we have the ideal input that we just saw and an actual input for the same ship's wheel program. So here, a few things that I want to point out is that sometimes what happens is semantically equivalent expressions can be written in syntactically different ways. Sometimes if you have a no-op expression, for example, rotation by 0, it is just omitted in the actual input, but it actually can be really helpful to have it because it helps you recover some kind of structure. And also, these expressions can appear in arbitrary order. So because of all these weird problems, we can't just directly apply the algorithm that we saw before. What we need to do is interleave that strategy with some CAD identities that can at least make all the sub-expressions have the same structure. Now, if you try to do it in a naive way, it doesn't quite work because of the phase ordering problem that we saw in the previous talk. So, arbitrarily picking some order of applying the rewrites isn't going to work. So instead, what we're going to do is use the eGraph data structure because eGraphs are really good at overcoming the phase ordering problem. So in the previous talk, we saw how eGraphs are really good when you have syntactic rewrites. But as Max was saying, they can be really powerful, and you can actually plug in a lot of different types of solvers with eGraphs to make it a much more powerful rewrite system. So here we're going to see how we can integrate a custom solver with an eGraph. So right now we are looking at the eGraph for this outer list that is appearing under this fold union, right? And then, as I was describing in my previous slides, what we do is we apply this structure finding algorithm. And when you do that, you introduce a map2 in the same E-class that has that outer list. And the children of the map2 are this rotation, a list of the parameters of the rotate, and the list of the CAD arguments. Now, once you have separated these out, you can send these parameters to a custom solver, and the solver tells you that you can rewrite them using this compact notation, and then you have to put this expression sort of back in the eGraph. And in order to do so, we are going to introduce an expression called a tabulate, which essentially is going to have a little bit more information in it to bind this variable I. And then the interesting thing that happens at this point is that the original list of the parameters gets unified with this new tabulate expression. Now, what does that mean? What that means is that this tabulate is equivalent to the original list of parameters that we started with. And because of that, you can put them in the same E-class, or you can unify those two expressions. So this is really great. And once you've done that, you can imagine having some kind of cost function, that gives more, gives more weight to the tabulate expression, and then you can extract a small program from this eGraph. But there's a little bit more to it. So as I was saying earlier, sub-expressions in the outputs of mesh decompilers can appear in arbitrary order. So what does that mean for this example? So it turns out that the rotation expressions in this program can appear in any order. They don't have to be sorted by their parameters. So here's an example where they're just appearing in an arbitrary order. So if you have this kind of a program, and if you try to apply the strategy that we just saw, you'll notice that these parameters that we have separated out, they're not sorted either. So if the solver needs to find this compact arithmetic closed form, first it'll have to sort the list. But if you sort the list, then you can't unify it with the original list anymore, because a sorted list is not equivalent to the original list. So what do we do? So a simple naive approach would be to just add all the permutations of the list of rotations in the eGraph. What can happen, right? Like we can just try them all, have them all in the eGraph, and hopefully one of them will work. But that is actually not a very good idea, because now you have exponentially many expressions in the eGraph, and that can cause the eGraph to be really, really big. And we don't really want to work with that kind of a situation. So instead, in Salinsky, we have this really clever trick called inverse transformations. The key insight of inverse transformations is that now the solvers are allowed to speculatively transform their inputs if the transformation allows for a more profitable rewrite in the future. So let's go back to the program and see what that means. So, our goal is to go to this tiny program that we have at the bottom right corner of the slide. And we have right now this big program that has all the rotates in arbitrary order. So once we apply the structure finder, we separate out the parameters of these rotates from their CAD arguments, and then we send them to the solver. And because of inverse transformations, the solver can now sort the list, and it can find this tabulate expression. The only catch is that before it introduces the expression back in the eGraph, it has to annotate it with the inverse of the transformation it did. And in this case, the inverse transformation is essentially the permutation that the solver used to get that expression. So what does that mean from the eGraph point of view? So instead of unifying the list with the tabulate, we unify it with this unsort. And because the unsort undoes the transformation, this unification is sound. So now what we're left with is this program that has the tabulate expression, which is good, but we also have these unsort and sort and all these kinds of transformations sprinkled in the program. We don't really want them in the final output, so we use a few other syntactic rules to propagate and eliminate them. So this shows you how we can use inverse transformations to flexibly combine arbitrarily complex solvers with an eGraph to make a really powerful rewrite system. And I want to talk a little bit about a few results that we have found from this from Salinsky. So we composed Salinsky with a few mesh decompilers, and these are the results of composing it with Reincarnate, which is a tool that we had built previously. And as you can see, the results are much smaller, right? So once you run Salinsky, you can get significantly small AST sizes. Another thing we tried to do was experiment with the scalability of Salinsky. So to do that, we went to this popular website called Thingiverse, and we downloaded all the customizable models from Thingiverse. So customizable is a group of models that are written in a programmatic form. And we ran Salinsky on all of these programs, and we found that Salinsky was able to operate on all of them in less than 1 second. That was really cool. And we have a lot more results in our recent PLDI paper. And if you have more questions about this, you can ask me offline. But yeah, that was it. I just wanted to talk about this tool that we built, and it can do some really interesting things. Thank you.
All right, very good. Let's virtually clap for Chandra. And Martin is going to be talking about objects that you cannot print or grab or hold in your hand, the objects that we use in software and verifying their construction. Martin Kellogg, take it away.
Thanks, Dan. So yeah, as Dan said, today I'm going to be talking about verifying object construction. And another way to say that is how we're going to use the builder pattern with the type safety of constructors. This is joint work with my collaborators here at UW, as well as at UC Riverside and AWS. So in an object-oriented language like Java, you might have a class like the one that's on the screen here with a mix of required and optional fields or parameters. Right? So this user identity, for example, has a name and an ID, both of which are required for some reason. That is, you can't have a user identity without having those things. And a nickname, which is optional. So some user identities have it and some don't. And in a standard construction, when you're actually building one of these objects, you'd usually write some number of constructors. So for example, for this class, you might have two constructors, one that takes just the two required parameters, and another that takes the two required parameters and the optional one. And this will initialize all the fields, and you'll have an object that's ready to go. But what happens if you do this wrong? So if, for instance, you accidentally try to create a user identity that only has a name, then the Java compiler is going to very helpfully tell you that you can't do that. It's a terrible idea, and you should feel bad about yourself. And it'll stop you, and you'll never actually be able to run that program. And that's a good thing. And that shows like the great thing about constructors. Right? They give you compile time verification that the arguments to the class are sensible. You're never going to construct a malform object. But constructors also have some downsides, and those downsides leads actual programmers to use other ways to construct objects. Some of these downsides are that the user has to write each constructor by hand, and if there are many optional parameters, that will be a lot of them. In fact, exponentially many, which is very uncomfortable. And the arguments are positional, right? So it's often hard to read code, and that leads to things like named parameters in Python. But there are many languages that don't have them, Java being one example. Right. And to avoid those problems, in languages like Java, programmers often turn to design patterns such as the builder pattern. And the builder pattern, basically what you do is you construct a second object or class that lives inside your first one. That's called a builder class. And the builder class has a setter method for each of the fields. So it has a name, an ID, a nickname method, each of which take that argument and then hold it. And then eventually it has a build method that actually constructs the object. And this looks like a lot of boilerplate, but it's going to actually be automatically implemented by a framework for you. And it gives you much nicer client code. It's very readable and very flexible. So the client, when they're actually constructing a user identity, writes code like this. They say user identity.builder, and then they call the setters in any order. It's very easy to read. You can tell which thing is the name, which is the ID. You don't have to worry about the ordering. And then eventually you call the build method, and this is very clear. Right? But let's return to the situation where the programmer makes a mistake and leaves out something. Right? And in that case, you have like that. So if you wrote like this, you just say name with the username. What's going to happen? Well, the constructor isn't going to catch this. Right? In the best case, your code is safe and is well written and very defensive, and will catch this at runtime. Maybe it'll throw a null pointer exception or an illegal argument exception if you're in Java, right? And that's bad enough, right? It's very unpleasant when your code crashes at runtime. You'd rather find out at compile time. But in the worst case, maybe that thing is like a password or something, and instead is initialized with like an empty value, right? And in that case, you could end up with like a very nasty security vulnerability that you only find out about later on down the line. And that shows you sort of the advantages and downsides of the builder pattern. So the advantages are that it's flexible, it's easy to read, and you can, as I said before, there are many frameworks that exist for languages like Java that will implement this totally automatically for you. But the downside is that there's no guarantee that the required arguments are actually provided. Right? So the programmer is free to call things in any order and to call any combination of things. So it's great for optional parameters, but you might have missed out on something that was actually important. And this is a real problem in practice. So on the screen, I've got some screenshots from the GitHub issue tracker for the Lombok project. And Lombok is a framework that implements the builder pattern in Java. And all of these screenshots are people asking for a way to enforce that some required parameters are actually provided. And the lead of the project said that they get this feature request every other week. And that was in a blog post he wrote about why this was too hard and they weren't going to do it. But what we've done in this work is we've showed that it is possible. And we can provide the type safety that you get with constructors. But we're going to keep the advantages of the builder pattern. So we're going to use the exact same code, but we're going to get the code to actually be checked and checked for correctness at compile time by the compiler. So how do we do it? Well, the natural way as a programming languages expert is to build something called a type state analysis. Right? And in a type state analysis, what you do is you construct a finite state machine for each of the builders in the program, and then you track it using a static analysis. So for the user identity example, you'd construct a finite state machine like this. You can see that it has a start state, and then you can reach states where different methods have been called and different arguments have been provided. And then once all the required arguments are provided, you reach an accepting state. And only in that accepting state is it allowed to, or are you allowed to call build. And then there's also a trap state or failure state that leads to an error being issued if you call build too early. Right? So this does work, but it has a big downside, which is that type state analysis in general is quite expensive. Right? In the arbitrary type state case, you need what's called a whole program alias analysis to make sure that your analysis is sound. So that is to say, in order to not miss errors, you need to be able to know that you need to know all the aliases in the program. You need to know which builders are actually the same builder, so you can keep their finite state machines in sync. But we notice something very important about this finite state machine diagram, which is that all of the transitions are flowing in one direction. There's no state that lets you escape from the final accepting state and go back to a non-accepting state. And the lack of that state allows us to define a special type of type state analysis that we call an accumulation analysis. And in these accumulation analyses, you're just building up more things until you eventually reach the good state. And accumulation analyses have really nice properties. In particular, that it's always safe to under-approximate, which means you can forget information, which means you don't need the alias analysis for soundness. And because the alias analysis is the very expensive part of an arbitrary type state analysis, that means that we can implement it modularly, right? Which means it's going to be much more scalable. And in particular, we can implement it as a standard type system without the type state bit, which is going to be very advantageous, right? It's going to provide the same guarantees that you get before. You don't need the alias analysis, and it's modular, which means it's going to scale very nicely to large programs. And you can use standard type inference techniques to reduce the need for human input, right? So humans don't have to interact with it very much. And this leads in the end to a specification for build for our user identity example that says you have to have called the method's name and ID before you call the build method, right? And so in Java, you'd actually express it using a type annotation like this. And in our actual implementation, this annotation is almost always inferred automatically using standard type inference approaches. So we evaluated this in 3 ways. So we built the thing, we evaluated it in 3 ways. And the first was to detect security vulnerabilities. So this is similar to the password example I gave before, where if you didn't provide something, then you would be vulnerable to an attack later on down the line. And we analyzed about 9 million lines of code. And in those 9 million lines of code, we found 16 actual vulnerabilities with only 3 false positive warnings. And we had to have a human intervene to write a type annotation only 34 times. So we think these are really fantastic results. In a second evaluation, we did a small user study with 6 industrial developers. And these developers were using Lombok, the tool I mentioned earlier that generates the builder pattern for you. And we asked them to add a new required field to a builder and then update all the call sites in the program. With our tool, all 6 were able to succeed at this task in under 5 minutes. But without it, only 3 of the 6 were able to at all in a 1-hour time limit. And those who succeeded at both were 1.5 times faster with our tooling. And they told us it was easier to have the tool report the issues at compile time, like way better. So developers love it. And finally, we did some case studies on both Lombok and another tool that generates these builders, Google's AutoValue. And we verified 653 calls to builders and found one that was unsafe. That one was in the Google GAPIC generator project. And the Google engineer, one of them who responded to our bug report, told us that our static analysis tool sounds truly amazing, which is always great praise to hear. And in that work, we needed 131 human written annotations, and we did run into 14 false positives. So that's it. It's possible to do the static safety of constructors with the flexibility of builders, which is an awesome result. And we found this special case of type state called accumulation analysis that doesn't need whole program analysis for soundness. And this work is now integrated into a tool called the Checker framework that you can find at this URL. And it's called the called methods checker within that. So I urge you to check it out if you're writing Java code. That's it. Thank you.
Thank you, Martin. Everyone can find their way to sudo applause as we switch over to our last talk. I'll remind you that we will take queued up questions in the chat after this last talk for any of our speakers. And with that, we'll turn it over to using concepts in program synthesis for creating data visualizations. Go ahead, Chenlong, take it away.
Yeah, hello everyone, I'm Chenlong. So basically today I'm going to talk about like visualization by example. So it's visualization we can see from everywhere, right? Basically like people in business, people in social science, everyone is creating visualization. So this just brings us a little bit thinking about actually what is visualization and how people create visualizations. So if you have taken a visualization class, you sort of know the visualizations are essentially like transformations from the symbolic, from data to geometric, to things that are going to appear on canvas. So this is one of the classical definition. So just assuming writing a little bit in a term style, you assume you have a table, that you're going to write a program that maps the fields of the table to geometric objects so that you're going to create a visualization. So as a simple example, if you have a data set with 2 columns, A and B, and if you specify a program that maps the column A into x-axis of bars and map the column B to heights of the bars, then you get a bunch of geometric objects. And if you render them on the canvas, you're going to get a bar chart. So this is pretty obvious. So however, in practice, just using this kind of like simple, neat idea of creating visualizations using mappings is not always going to work very well. So the problem is that just assuming you have a slightly more complex table, instead of having only X and A, you have 3 other columns. And instead of want to create a bar chart, you want to create a stack bar chart. You want to create a 1 color for each bar and stack them together when they have the same x-axis values. So this just makes it a little bit trickier to think about how do we specify visualization in a mapping form like we described before, because the new visualization design is expecting a certain shape of the data, that one creating x-axis, another creating the height, another creating color. So this is actually what happening in practice, is that you don't really just need a mapping to create visualization, but you need an adapter to adapt the data so that you're able to specify the visualization in this way. So now let's given the same data set we have. So instead of directly specifying the visualization, we're going to first transform the data using an operator called pivot longer. This operator essentially just gathers the fields from the data set, like transforming the columns into 1 column called key column. So that essentially like make the table much longer, but also a little bit narrower. So after this transformation, the visualization specification is pretty clear. We're going to map the first column into x-axis of bars. We're going to map the value column into heights of the bars, and we're going to map the column headers into the colors of the bars. So this basically just allows us to create this stack bar chart in a pretty clean way. So in practice, so essentially the data adapter just prepares the input table to match the data layout. So in practice, like we solve those data visualizations, we solve these transformations using a Python or whatever libraries we're familiar with, and we can create a visualization through those mappings using ggplot, or if you're from UW, you probably use Vigolite a little bit more. So, but for like, this is not a problem for us like professional people who know how to write programs. But for people who are like data scientists or business people, not all people has the ability to write everything in program. And also in their job, they often have those diverse data layouts coming in practice. And like writing programs specifying this transformation and mapping requires some software knowledge they need to get familiar with. And finally, if you want to specify a visualization with a little bit more complex concept, it's a little bit hard to specify because it requires you to have a little bit more design knowledge. So the real question here is that, can we have a way to allow people to create a visualization so that they can specify the visualization in an expressive way, but also in a layout independent way, so that we're going to shrink in the pipeline again, just don't require people to create those intermediate steps. So our solution is a tool called for Fox for visualization by example. So instead of asking people to write programs to transform data and visualization data, we're going to allow people to create a demonstration that demonstrates how a subset of the data points are going to visualize, and the tool is going to generalize the data and create a full visualization that visualizes a full data set. So let me show you a short demo here. So now that's just assuming we have a simple data set, we have a date, and we have the New York temperature, and we have San Francisco temperature. And all we want to visualize is to create a line chart of the San Francisco temperature, and also create a bar chart to show the temperature difference. Yeah, so this is a visualization. It's pretty cool. So let me show how we do this in a tool like we created. So first, we're going to upload the data into the tool. It's clearly what we can see here. We have the date as one column, we have New York temperature as one column, and San Francisco in one column. So you can see this tool has no place to type in programs, so we're not going to create programs ourselves. What do we do? We're going to demonstrate what we want to do. So if you recall the goal, we're going to first create a line to visualize the San Francisco temperature. So what we can do is just build a simple line segment to show the San Francisco temperature in the first 2 days. So this line essentially will start from the October 1st and then end in October 5th. And the San Francisco temperature in the first day is like 62, and the second day is 58 or something. So in this, we create a very simple line chart that shows the San Francisco temperature change over the 2 days. And another goal is to create a bar chart to show the difference, to highlight the temperature difference between the two. So we're going to create a small bar to show the temperature difference exactly on the first day. So we can just create this bar, essentially a position on that day. And it should start from the San Francisco temperature and ends the New York temperature. And the temperature difference, if you calculate, is like 0.7 here. So this is essentially a minimal visualization to visualize what we want to do. And now we can tell the tool, can you make an induction on the demonstration to figure out how to visualize the full data set. And what we can do just through the tool and wait a few seconds and to see what the tool can come back to us. So here is actually, you can see the tool essentially create the bar chart and the line here to visualize all dates we have in the table by generalizing from this example. And of course, after this, you can do a little bit more tuning on tuning colors to make it looking better, or you can even add it in the underlying programs. But essentially behind all of those are the programs that perform data transformation and the script that visualize the data. Yeah, so this is essentially how the tool do. And now let me tell you a little bit about how the tool actually solve it. So given the algorithm, is that when user provide the input data and the miniature small visualization demonstrate the idea, the tool will first run a visualization decompiler to infer the visualization program behind this. And this is essentially trying to figure out what is a visualization they're going to use, what function is going to be applied. And after that, the tool goes into a data transformation synthesis algorithm that tries to infer how do we transform the origin data to match the expected data program. This is a little box to see. We're going to essentially a search program that given the data transformation grammar, try to figure out how to transform it. It's a small grammar, but it actually contains a lot of technical details, but we don't care right now. So, and after this, we're going to combine this synthesis program into a real program. So here I'm writing the program in R, if you know that. And when we have those real programs, we can just render in the interface, allowing user to inspect. Essentially, it's giving the user the opportunity to inspect whether the tool make a correct generalization of your demonstration or not. And this can just goes into a loop of development. Yeah, so we did some experiment, both in terms of the tool efficiency, how fast the tool can solve it. If you see my demo, it's very fast. So, and also pretty expressive. So we actually test on a bunch of tasks from online forums, people ask, and tutorials. And we actually see that we're able to solve a majority of them, and most of them can be solved in a small amount of time. And so there's some harder cases with large inputs, a bit harder to solve, or cases that require more arithmetic computation. And we also do a user study on 33 users, comparing how the experience of people using R versus our tool Fox. And on the 4 tasks we test, like there are 2 tasks where using Fox is significantly faster to complete the task. And people give some pretty interesting quote. It's pretty easy to learn and also good for prototyping. But people also giving some suggestion that it's pretty better to be used if we have deeper integration of other tools so that they can just like query data and create visualization in an easy way. So yeah, this is basically what I do. We create visualization from examples. And some ongoing directions, basically how to scale up the algorithm and how do we actually allow users to specify richer visualizations in a more interactive way, and how do we allow people to adapt the visualization. So yeah, that's everything. Thanks.
Thanks so much, Chenglong. We can all applaud. We have a few minutes for questions. I have to admit that so far, the first question from Paul Beam, I swear, Chandra, I did not plant him. He wants to know where the name Zelinsky comes from. And if you don't remember, then I'm happy to answer for you.
Well, no, I do. I can't forget that. So there's this movie called Honey, I Shrunk the Kids. And the main character in the movie, his name is Wayne Selinsky, and he shrunk his kids. So when Dan, when we told Dan that we're looking for a name for this tool, he was like, it has to be Selinsky because you're not shrinking kids, but you're shrinking cats. So that's why it's called Selinsky.
And he also, he wanted to know the other tool names as well, if there were any. And then, so he got egg because that was explained in the talk. Chenglong, you're fixing up the URL for where your tool is available. Excellent. And are there any additional questions from folks attending? We certainly do have time. Lombok is one of the, I see, Indonesian islands like Java. Fortunately, there are, hundreds, if not low thousands of them. So a steady source of names for Java tools. Great. So there's a question from Yasemin, whether your tool support, is the demo actually interactive? Can people try their own demonstrations online?
Yeah, it's recently hidden on the link I sent earlier in the chat because Sabina paper is hidden from Google search. So yeah, it's available to try.
Great. And then I'm going to keep plowing through. I think these are fairly short questions, so we can get through many of them. Ben Schreiber asks, any plans to, I'll reinterpret slightly, bindings for egg and other languages?
We have considered it. One of the difficulties is it's generic in kind of like the C++ template sense. Rust is a similar thing. So you don't know what language to instantiate it for. Herbie, which is one of the tools that uses egg, is written in Racket. And the way they do it is they have a shim that is 300 or 400 lines of Rust, which basically tells egg about the language that it's interested in, and it's very easy to write C bindings to that language once it's kind of been stamped out. So that's how I would do it.
Good. Chenglong, this next one is for you. Jennifer Mankoff asks if the tool could generate accessible text to make the resulting visualizations accessible.
Yeah, I think it's possible. So one of the components is basically how to decompile visualization into a program. And essentially, if we know the program, we know what's the visualization is talking about, and we can translate that into text description of the visualizations.
Okay, great. Well, excellent. In the end, a set of good questions, 4 great talks. Thank you so much both to our speakers and to everyone listening. I believe next week we take a break from this format and have our first distinguished lecture of the fall. Looks like a very interesting abstract you can find on the Allen School homepage, www.cs.washington.edu. For the Pulse group, that would be uwplse.org. No hyphens. I'm told in the group's history that hyphens reek of desperation. And thanks so much for coming, and we'll see everyone later.